Hi, this is Zhenlan Hu. I'm a student at Introduction to System Engineering. I'm very glad to be here to present my final report. The topic of my research is about understanding the system engineering by doing a case study on SpaceX innovative Falcon 9 rocket. And during this presentation, I'm gonna introduce the life cycle of Falcon 9 rocket development, including design, manufacture, integration, testing, and launch. Before we get into the second half of the report, I'm going to do a quick recap of what's in our midterm report and do a quick review of what I have learned so far in this course. The trend of the system engineering. So the system engineering is a long existed and well-developed engineering discipline. It is a developing forefront because of technological advance. System engineering is actually a very old subject. It has existed for a long time. However, due to the technology advance, engineers keep refreshing their knowledge base and coming up with new methodology in compliance with policy, with regulation, and also, most importantly, to keep update. So by definition, we're moving on to the first stage of system engineering, which is the concept development stage. So by definition, the concept development stage embodies analysis and planning that is necessary to establish the need for a new system, the feasibility of its realization, and the specific system architecture perceived to best satisfy the user needs. A few important terms to mark out. First, there has to be a need for a new system, so there has to be a valid need. And the system has to be new. It cannot be something that's already existed. A short recap of SpaceX. So SpaceX was founded by Elon Musk back in 2001, and it was headquartered in Houston, Texas. The company's mission is to build rocket that can be reusable. So by saying reusable, it means after launching the rocket and completing its mission, the rocket can return back onto the surface of Earth. The most recent progress of SpaceX is its very advanced Crew Dragon spacecraft just docked with the International Space Station just a few months ago. And SpaceX was regarded a pioneer in private commercial rocket development and in manufacturing. So far, there are a couple of very advanced state-of-the-art rocket series, like Falcon 9 series. It's the most powerful rocket ever made by human being, especially the Falcon 9 Heavy. It has a very large payload delivery. Let's take a quick look at the different kinds of Falcon 9 rocket. So from the left to the right are the different generations of Falcons rocket developed by SpaceX. As we can see, the Falcon Heavy is so far the most powerful rocket developed by human being. And if we look at the bottom of the rocket, we can see the Merlin 1D engine, and we're going to mention this state-of-the-art engine shortly. And we can see the payload is on top of the rocket, on the upper half of the rocket. Okay. Concept development stage. So two things we want to address here. First is a need analysis, and the second, we want to make sure there is a practical approach exists to satisfy such a need. Okay, now moving on to the first part, it's a need analysis. I divide it into three sections. First, rocket reusability. Second, safety and reliability. And third, commercialization of rocket manufacturing. As I have shown in my final report, the rocket reusability is an urgent need by the current industry. The reason is straightforward. Like given the current economy model of rocket launching, it's simply not economical to launch a rocket and then get it wasted in the deep space. Because traditionally, after completing its mission, a rocket is either wasted or re-enter the atmosphere and was burned down into ashes, and this is obviously not economical. And second, safety and reliability. This is a long-standing criteria that we want to build a safe and reliable rocket to complete different kinds of missions. And third, there is a need for commercialization of rocket manufacturing. This is because a private company, the goal of a private company is to make profits out of its business, and it's usually less expensive to develop and to launch a rocket than state-owned agencies like NASA. A practical approach for SpaceX. The infrastructure for testing and integration. We know that SpaceX has multiple testing centers and facilities in across states of United States. So it has a large testing facilities in Texas, and has another integration in the testing states in the state of California. In the meantime, SpaceX partnered with NASA and other companies. Sometimes SpaceX even rent NASA's facilities, like in Florida, to launch its rocket. Reusability. So there is a practical approach to achieve this reusability feature. SpaceX add very unique techniques like green fins, gas thrusters, and they redo their fuel calculation to make sure that their rocket can do a flip in the deep space and then return its and then change its trajectory and get back onto Earth because of its advanced development in these techniques. And this has been shown to be a practical approach due to its several accomplishments. So far, SpaceX was able to launch its rocket and make its turn in space and landed the Falcon 9 safely on a landing site. The landing site can either be seaborne, or a landing site on land. A concept exploration phase. So the new system should be able to perform desired functions, and there got to be one feasible approach to achieving such performance at an affordable cost. Okay, just to do a quick recap on what I have discussed in my midterm report. So SpaceX wants to develop a new generation rocket that can achieve a few new features. So first, the Falcon 9 rocket should be able to lift payloads of significant weight, because we know the purpose of having a rocket is ultimately depends on its ability to deliver payload to either Earth's orbital orbit or to dock with International Space Station to deliver a cargo, those resupply mission. And second, we want to make sure that Falcon 9 can land safely and smoothly on Earth. And this is what we talked about earlier. It's about the reusability attribute. Third, Falcon 9's engine should be able to perform acceleration, deceleration, and instantaneous maneuver on its journey back to Earth. And this put a higher requirement on a rocket's engine. And we're going to talk about Merlin 1D shortly. Fourth, Falcon 9 should be equipped with engine out capacity. When one of the engine experiences technical difficulty, then the other engine should kick in immediately to fill its position. Fifth, action should be taken to improve the reliability and safety, and this is what we mentioned. The reliability and safety has always been a goal in space exploration. Sixth, the rocket should be designed as a two-stage rocket. And so this is a quick review of what the desired function are in when the SpaceX is developing its SpaceX rocket. And there has to be one feasible approach to achieve such performance at an affordable cost. Such action involve first, the engineer should design first stage booster in a way that rocket can restart ignition in the upper atmosphere. So basically, we have to have a restartable ignition system. Second, engineer need to apply new altitude control technology. So altitude control technology is something novel, and SpaceX has been doing a lot of development in this arena. And actually, we're going to talk about shortly that a few of the experiments that failed is because of the immaturity of the altitude control technology. However, SpaceX has done a lot of work in this area and improved this technology. Third, hypersonic grid fins. So hypersonic grid fins has to be installed in order to turn precision landing into a reality. So it all depends on this small but critical component called grid fins. Fourth, we have to do modification on Merlin 1D engine to reduce engine thrust. Fifth, Falcon rocket needs software support like navigation system, GPS, guidance, control system software. So as we can see that it's more than possible. So there is at least one feasible approach to achieving such performance at affordable cost. The function to be performed with this new system, so large payload, reusability is a key feature here, and the engine's power. I mean, the engine's power has to be pretty large when the Falcon 9 rocket launches because it has to deliver the payload. But once the mission is completed, the engine's power needs to be partially shut down. Otherwise, the rocket is gonna just crash landing onto Earth and engine out capacity. And we have talked about this software safety two-stage. Okay. And there has to be at least one feasible approach, and we just mentioned that. Do a quick review. So we have to have a restartable ignition system, altitude control technology, hypersonic, grid fin, Merlin 1D engine, software support. Okay, and we're gonna skip the first three components: relative performance, operational utility, development risk. Feel free to refer to my final report, and it has been laid out there. I'm gonna focus on the cost part. So the ultimate purpose of having a Falcon 9 rocket, given SpaceX is a private company, is because it's to save cost. So based on this graph, we can see Falcon 9 rocket. To launch a Falcon 9 rocket, the standard price is $62 million. This number may sound pretty large, but comparing to NASA's average cost of launching a rocket, this is actually this is much less expensive. and to launch a Falcon Heavy rocket cost roughly $90 million. And also the Falcon 9 series rocket is in fact the most powerful rocket ever being built by mankind. As you can see, the performance is very impressive. Like almost 22 metric tons of goods can be delivered by Falcon 9. Okay, moving on to what I have been researching, what I have been learning in the second half of the semester. So engineering development. By definition, engineering development strive to resolve the majority of uncertainties through analysis and development, and to validate the system design approach as a basis for full-scale engineering. So now we have done concept exploration. We had already figured out that what kind of product we want to manufacture, and we are pretty sure it's going to work. We have a general idea, we have a blueprint, and we already have a few goals, but now we want to put everything in practice. So we have to develop, use our technical skills, use our engineering techniques to really make a prototype and test that prototype to make sure it can fit all the requirements, to make sure it can meet all the specification before we deliver the product to our expected users. Okay, and this involves advanced development and engineering design. Going back to what we have talked about, so we're gonna talk about great things, cold gas thruster, landing legs, and Merlin 1D engine. Great things are essentially small, foldable, heat-resistant wings. So they are wings, and they're designed to steer the first stage rocket as the rocket begins its re-entry into Earth's atmosphere. So they're a kind of like a steering mechanism to make sure the trajectory, the speed, the direction of the first stage rocket is appropriate. Second, cold gas thruster. Cold gas thruster are a mechanism to flip the first stage rocket. So when the rocket was in space and complete its mission, we use cold gas thruster to to turn the first stage rocket 180 degrees. So now it's heading towards the trajectory that's gonna return to Earth. And we're also going to add landing legs at the bottom of the first stage rocket. This may sound very obvious technique, but these landing legs are made of carbon fiber. They are very lightweighted, but very strong. And the legs are usually deployed as the rocket is approaching a touchdown. And this is quite critical to enable a soft landing rather than without the legs, the rocket giving speed gonna crash land on the Earth. That's not something we want. So we want a soft landing to make sure the rocket it's still integral, still fit for a next mission. And another huge component is the Merlin 1D engine. The Merlin 1D engine basically, for a Falcon 9 rocket, just to be clear, it requires a set of 9 Merlin 1D engine to provide sufficient thrust to lift the payload. And we're going to take a look at the graph. We mentioned a few key points. So in the middle of this graph, we can see there is a flip maneuver part. That's when as you can see, the first stage rocket just flipped, made like a 90 degree or more than 90 degree flip, and then now it's on its trajectory to head back down to Earth. And during the return journey, it's gonna file a boost back burn, and the boost back burn is gonna bring the trajectory to the landing site. And then to achieve a vertical landing, it involves a mixture of hardware and software navigation system. And this is the Merlin 1D engine we have been talking about. It's a set of 9 uh, identical engines. The reason why it's 9 is because the total thrust or the total power has to be sufficient to lift the payload, but also there has to be some extra reserved power, just for contingency purpose. Just when during launch, if one of the engine is not functioning properly, the other one can quickly kick in and provide sufficient thrust. Integration and evaluation is the next step. So after advanced development, now we need to test that what we have just developed is what we need or can meet the requirements, the specification required by our customers. And we have learned that all components that are deemed insufficiently mature for full-scale engineering should go through development and validation stage, and these are for the insufficiently mature techniques. But even for components that are listed as sufficiently mature, these components still need to be validated through analysis or test prior to their acceptance for engineering. So basically what this is saying is, basically for all those components, as a system engineer, you have to test them. You have to evaluate the integrity when they are integrated together. And even for a few components, they are old technology, they should be working, they should be fine, but when you are put them together on a higher level, on a system level, you're not sure what the impact on the system. So we need to make sure that they are still functioning well with the other components. So the bottom line is test everything and evaluate the impact. Okay, the 2 steps. The first is the prototype development, and the second is the development test. In the prototype development, the system engineer need to identify issues of physical implementation involving unproven technology and determine the level of analysis, development, and test required to reduce risks to acceptable values. And system engineers, along with component designers, so those are people who are specialized in each technical field, develop and build prototypes of critical components and subsystems. Engineers conduct tests and evaluation and correct deficiencies based on feedback. Second, development testing. The system engineer need to create feasible test plans and criteria for evaluating critical elements. So first, as engineers, we have to know what required performance or specification before testing on unproven technology. So basically, for example, when we are talking about engine design, we need to know the thrust of power each engine can provide, or we hope them to provide, and the fuel consumption per minute. So those are the metrics we're going to evaluate when we do fire testing. And after having plan and evaluation criteria in mind, we're going to conduct tests of critical components. This testing is a long process. It involves several rounds and may continue through the entire product development cycle. And based on the feedback from testing, we're going to change the original design, or we're even going to go back and change the requirement, because sometimes the requirement is just not realistic or has some errors based on calculation. So we use testing to correct our expectation. But for the majority of the time, the first few trials, the first few testing are not going to meet the specification, and then we're going to go back and redo our advanced development, modify our designs, and hopefully by the next time that we can beat the metrics. Okay, to assess the maturity of components, we look at the following 4 standards. First, functional interaction. Second, physical interfaces. Third, if there is human operator involved, we need to look at the human-machine interface. And fourth, we consider other environment factors. Okay, we're going to talk about two examples from recent testing or recent incidents from SpaceX company. The first is a incident involving insufficient hydraulic fluid. As we talked about earlier, the hydraulic fluid is used to steer and control the rocket's descent trajectory and motion. And at one time, there was insufficient hydraulic fluid. And given the insufficiency of the hydraulic fluid, the mission did not succeed. So the development team decided to equip the first stage with much more of this important fluid for purpose of steering the rocket. This is a very simple solution because getting the feedback that we need more hydraulic fluid, the engineer decided to put more fluid in the tank. But system engineers had to be careful that by adding actual weight of this hydraulic fluid, what's its impact going to be on the other components? Are we going to do the recalculation of the entire fuel consumption? Are we going to change the design of the fuel tank or change the design of the container that hold this hydraulic fluid? So if we change this thing, then there are going to be other successive impacts on the system as a whole. The second incident involving a throttle valve. So basically, the incident is about roughly about 10 seconds before landing. A throttle valve failed to respond to mission control's command as fast as it should be. So it responded a little bit slower. The valve functions to control the rocket's engine thrust. So by not responding to the command to slow down, then basically the rocket was descending too fast. And there was no time to readjust or recover this fast landing. So then the body tipped over. It was not successful or soft landing. Though reusability was not accomplished in this instance, the body tipped over, so basically it damaged itself. The rest of the process went as planned. So the only issue here is why. We have to figure out why the throttle valve was not responding to the navigation's command at the moment. And there are other examples or other incidents, other failures from SpaceX, and they give valuable lessons to the testing engineers, to the system engineers about the problem with the current system, the problem with the components, and now the engineers have to find a way to fix these deficiencies. Production. So moving on to the production stage. By definition, so this means that the company is ready to manufacture its designed component. The company intends to manufacture identical sets of hardware and software components and to assemble each set into a system suitable for delivery to the users. A subplan of production planning are listed here. First, responsibility and delivery schedule. Second, manufacturing sites and facility. Third, tooling requirements. Fourth, factory test, and so on. I'm not going to read everything out, but I'm going to focus on a few of this. So I'm going to talk about the second and fourth, the manufacturing sites and factory test equipment. We're still going to go back to the Merlin 1D engine. So it might be. So many people might think that, oh, the engine is built in-house at one facility. It tested out, integrated, and then ready to launch. That's not the case. So the reality is the Merlin 1D engine is built at the headquarters in Hawthorne because it's a very important component. I mean, the rocket depends on a good engine. So it's developed at the headquarters. And there is a huge production team there with very advanced testing site, rocket development facility. And the facility is over 4,000 acres. In another place called McGregor, Texas. So the testing site is already separate from the manufacturing site. And that's one thing. And then next, we're going to move on to parts integration because engine is still a big system. There are different parts. So like gas generator, turbo pump, injector, thrust chamber, or valves, just to name a few. And each component is developed by their separate production team. And now we move everything together to put it into integration. The various engine components and subparts are integrated to form a larger system. And if I remember correctly, there are another production team and testing or evaluation teams in another state, and they communicate with each other about their design, about testing results, and possible fixes. Challenges. So I have learned based on this case study that there are many challenges from system engineering perspective. First is from system engineering perspective, a rocket development is a big project. It involves thousands or even hundreds of thousands of people, engineers, management, suppliers. And as a system engineer, we have to think about the higher level, the integration of different components of different subsystems. And it's about communication. It's about how to collaborate with others, and always think about a small fix on certain component can have an unexpected impact on the other components, and integration testing or all sorts of things. I mean, even there are so many smart people, engineers working in SpaceX, but sometimes we heard in the news that a launch was not successful, the landing was not a soft landing, and etc. And also, second challenge is heavy regulation imposed by FAA and U.S. Congress. From my final report, as you can see, that up to today, rocket or space exploration is still heavily regulated, and it's restricted. I mean, certain areas are still restricted to state-owned, like NASA, like state-owned agencies, and they are not completely open to private companies. And there was actually a lawsuit, a legal battle back in 2014. So the legal battle basically is SpaceX filed a lawsuit against the U.S. Air Force at court. It's about a block buy contract. So SpaceX claimed that Air Force did not give the company a fair chance to bid for certain lucrative launch contract, and Air Force only awarded the contract to its long-existing partner, the ULA. And ULA has certain relationship with Boeing company, and ULA is actually at the time was the only company that's allowed to bid for the contract, and SpaceX finds it's unfair. It's not open to the market to bid for the contracts, but it's like awarding to its own partner. It's very restricted, and competition from government space agencies. So NASA is a collaborator, a partner, but obviously a competitor to some extent, because NASA has its own facility, has its own manufacturer, production ability, and we are not sure whether NASA is sharing all those technology details or share all those suppliers, the customer list with SpaceX. Summary and lessons learned. So there are a couple of lessons I learned from this case study. So first, system thinking. Component thinking is good, but it's not enough. And for a system engineer, just think about component is not enough. We have to think on a higher level. Integration, evaluation, testing. So always do testing, evaluation, and when you get the results, don't be disappointed. The first few trials gonna probably like 95% going to be failures. But what's more important is learn from the failures and do fixes. And when we apply fixes to the existing system, we have system engineer has to make sure that they are learning things, that they have to know what the impact going to be on the other components. Okay, to conclude. So basically, what we have here is a very successful private space exploration company, SpaceX. A few years ago, it has already launched its rocket, and the reusability now is more than possible. It's a reality. So, but we still are left with certain uncertainties. So, for example, Elon Musk, the CEO of SpaceX, has eagerly claimed that his rocket can fly 100 times, but based on the data we have, each Falcon 9 rocket can fly like single-digit times. So to make reusability fully feasible, there's still a long way for SpaceX to go. But we also have to look at the successes, the huge amount of accomplishments that SpaceX has contributed to the industry, to the mankind. So the system engineer is obviously a fundamental part in its success. SpaceX has spent thousands of millions, billions of dollars on research, on development, to sharpen its methodologies, to update its knowledge base, and hire new talents. But maybe one thing to keep in mind is SpaceX is ultimately a private company, so the goal is to recoup its investment and to how to make it profitable, so that SpaceX can have the money to invest in its future. Okay, thank you for watching.